Hello, I'm Professor Stephen Abbott. Welcome to IGC, Inverse Gas Chromatography, what it is, what it does via apps. And this is the fifth of 4 videos on IGC. Why the fifth of 4? I recorded the 4 and then realised that there was one extra message that I needed to get across about how best to do IGC in practice. Let's go straight to, not the app, but the web page. So, what I want to describe is the optimal way to do IGC. It's very simple in practice, and in the apps I make it sound very simple. You just measure the retention times or you measure the peak width and all's fine. But I've looked at lots of IGC data, and although I'm not an expert, it's clear that a lot of published data is at best wrong and at worst awful. So we need to be able to do IGC in the best manner to get the best possible data. And the first thing is to have a good set of probes. Many people do tests with, for example, hexane, heptane, octane and nonane, and then say methanol, ethanol, propanol, butanol. That's 8 experiments, and sometimes you get value from that, but really that's doing the same experiment twice, because there's not much difference between hexane and nonane, and there's not much difference between ethanol and butanol. If you did the experiments with, for example, hexane, toluene, chloroform, MEK, acetonitrile, ethyl acetate, pyridine and ethanol, you'd be scanning a whole range of chemical functionality, and you might be able to extract much more meaningful data from those same 8 experiments. The next point is about infinite dilution. The apps used on this site assume infinite dilution. This means that the probe molecules interact only with the support medium and not with each other. This means you have to have a short, sharp peak of low intensity, and therefore you need a good detector to be able to do it. But even if you have such an ideal injection, there's a problem. At the start, you have a high concentration at the center of the peak, and this may well exceed infinite dilution. As the probe goes down the column, the peak widens and gets shorter, and that's for 2 reasons. The widening is, of course, some fluid dynamic effects, flow effects, but also the absorption of the probe onto the support helps it linger, reduces the concentration in the gas phase, and therefore you get closer and closer to ideal. So this part of the experiment is closer to ideal than that. So when you do the analyses, you have to take this changing in ideality or in infinite dilution as it goes down the column. I just need to note that some IGC uses finite pulse, where you have a large concentration and it's a broad peak, and you watch how that declines over time. Not discussed in these apps, but an important technique. The shape of the peak at the detector does give a lot of extra information. Even if you're just looking for retention time and peak width, if you actually know what your peak shape is, you can get extra information about how good your data are. Because you want the peak shape to reflect the science, you don't want it distorted by other things. And these other things are, for example, input-output tubing. If you have a long length of broad tube, that will make the peak broaden out. If you have dead space in the column, of course that would make the peak widen for unnecessary reasons. In IGC, you want to put in just the right amount of material to get the best analysis. And if you use just one column size, then the chances are that you will have too little material in for some experiments, therefore you have a lot of dead space. So it's very important that you have a lot of different sized tubes so that they're optimally packed for different experiments. And the packing also makes a difference. If you just throw the stuff in, you'll have a lot of voids, loose packing, and you'll have a lot of peak spreading. So you need to pack it properly via tapping, vibration, or ultrasonics, whichever actually works. That's an art in its own right, but you need to do all those things to ensure that the peak shape is as perfect as possible. Of course, in all GC you adjust the flow rate, but in IGC it's very important that you can tune the flow rate automatically. So for example, for diffusion measurements, you need to do the experiment at a set of different flow rates. And as we'll discuss later, if you flow too fast for some experiments, you don't get equilibration and the data is meaningless. If you flow too slowly, then you are using up unnecessary time. So it's important to have the computer-controlled rate of flow so you can do a few quick scouting experiments to get the optimum flow rate. I won't discuss the oven and detector, that's obvious. You need to do your experiments intelligently. As I hinted above, if you go too slowly, then you're using up valuable analysis time. If you go too quickly, you are not getting proper equilibration. So you need an intelligent understanding of how your probe is interacting with the support to know whether you've got the right flow rate. And whatever you're doing, think through the assumptions behind the algorithms used to obtain the data, and then make sure your assumptions are valid. When you're analysing the data, it's important to not just get those bits of information which directly give the analysis, like retention time, but, as I said above, to look at things like peak shape, which give you all sorts of secondary information, but useful nonetheless. So you need good data analysis capabilities to be able to assess not just the numbers that you're interested in, but the quality of those numbers. And this brings us to the fact that I hinted at the start, that in published IGC work there's a lot of bad data, bad science and bad software. And I can speak personally from that. When I became interested in using IGC for Hansen solubility parameters, I started with some data sets which happened to be by Monk and by Volkel. I didn't know it at the time, but these were excellent high-quality data sets, and it was very easy to get the analysis right to derive HSP parameters. When I started looking at other data sets, I often got junk results. Well, I'm not an expert, maybe my software was bad. When I checked my software very carefully, I in fact found a bug. Very embarrassing, but it turned out that bug did not affect the general ugliness of many of the data out there. I then realized this point about people going too quickly so they didn't have equilibration, and they were also using solvent data sets like hexane, heptane, octane, nonane, and methanol, ethanol, propanol, and butanol, which weren't actually providing enough chemical data to make a valid HSP analysis. Finally, I found a colleague who had some excellent high-quality data sets. My software had been validated, and yet the results were still nonsense. That's when we examined all the assumptions, and there's one assumption that had been made all along, which was that the support was neutral. When my colleague checked the assumption and changed to different support, suddenly all the data made a lot of sense. It turned out the previous support had not been neutral. And going back to the original Monk data, I discovered that he'd paid a lot of attention to choosing the right support, and others had not followed his lead. Your own experiences will be different, but the process is the same. Are the data bad for some reason? Is the science bad for some reason? Is the software faulty? In other words, as with so many other things, IGC requires you to be a good scientist and to question your assumptions.